We present efficient view synthesis and 3D-based multi-frame denoising with multiplane feature representations. Our method unifies view synthesis and multi-frame denoising under a single framework relying on multiplane features, a new volumetric scene representation generalizing multiplane images to feature space. The inputs to our method are a number of clean or noisy images projected into plane sweep volumes using standard plane-induced homographies computed from camera parameters. These plane sweep volumes are processed in a depthwise manner using a shared encoder, producing a multiplane feature representation of the scene. The multiplane feature representation is then back-projected to an arbitrary number of viewpoints before being processed by a shared renderer, producing synthesized or denoised outputs. The current state-of-the-art in multi-frame denoising relies on two main components: bidirectional recurrent processing and 2D-based flow-guided deformable alignment. It is computationally efficient and works on casual videos with object and camera motion, but it suffers from a lack of 3D consistency across frames, especially at high noise levels. Recently, a new paradigm treating multi-frame denoising as a view synthesis problem has started to emerge. In this new paradigm, noisy images are used to train a neural radiance field representation of the scene. The cross-view consistency enforced implicitly ensures that the representation is noise-free, and clean output views can then be resynthesized using the camera positions of the input views. This approach produces outputs with high 3D consistency, but it is computationally heavy and it tends to overfit some residual noise in the input views. As a proof of concept, we apply Gaussian noise to the Lego truck synthetic scene and denoise it with a 2D-based state-of-the-art method and with a 3D-based nerf. We see that the 3D-based nerf produces results that are more faithful to the underlying geometry of the Lego truck, motivating the use of 3D-based methods for multi-frame denoising, but the output images still contain a large amount of residual noise, and the nerf model is orders of magnitude slower to run. In this work, we use a different approach inspired by multiplane images, or MPIs. MPIs are volumetric scene representations for novel view synthesis decomposing the light field into a stack of semi-transparent colored layers. The MPI framework is much lighter than the NERF framework computationally and generalizes to new scenes. It can handle few input views in a forward-facing setup and relies on the same convolutional building blocks as classical 2D-based multi-frame denoising methods. The standard MPI pipeline implements four successive operations: forward warping, projecting the input views into plane sweep volumes; encoding by an MPI prediction network, producing the multiplane image representation; backward warping, projecting the MPI back to an arbitrary number of novel views; and rendering of the output views using the fixed overcompositing operator. The only learnable module in this pipeline is the MPI prediction network, MPINet, which typically struggles to predict multiplane representations that are self-consistent across depths from multiple viewpoints. This problem can lead to depth discretization artifacts in synthesized views and has previously been addressed using a large number of depth planes and computationally expensive mechanisms, for instance by iteratively refining the MPI using learned gradient descent in deep view. Here, we solve the cross-depth consistency problem in a novel way by addressing it at the rendering stage. Specifically, we replace the fixed overcompositing operator with a learnable renderer, enforcing consistency directly at the output level on a per-view basis. This design change has three important implications. First, the encoder module can now process depths independently from each other and focus on fusing information across views. This significantly reduces the computational load of the encoding stage. Second, the scene representation changes from a static MPI to multiplane features rendered dynamically. This significantly increases the expressive power of the scene encoding. Finally, the framework's overall performance is greatly improved, making it suitable for novel scenarios, including multi-frame denoising, where it outperforms standard 2D-based approaches at a fraction of their computational cost. We first illustrate our method on the spaces dataset in an overview synthesis scenario using the large baseline setup. In this setup, each method receives 4 clean input views and synthesizes 9 novel views for 10 validation scenes. Our multiplane feature encoder renderer significantly outperforms Soft 3D, Deep View, and 3 other standard MPI baselines. We then consider a multi-frame denoising scenario in which each model receives 16 noisy inputs and synthesizes the same 16 views for 10 validation scenes. We use a synthetic noise model following a signal-dependent Gaussian distribution with a gain level of 20. Our multiplane feature encoder renderer significantly outperforms state-of-the-art 2D-based methods, VBM4D, BPN, Basic VSR++, and DeepRep. We then move to the real forward-facing dataset and again consider a multi-frame denoising scenario in which each model receives 8 noisy inputs and synthesizes one of them for 43 bursts extracted from 8 validation scenes. Our multiplane feature encoder renderer significantly outperforms 2 existing 3D-based methods, IBRNet-N and noise-aware-nerf. Finally, we consider a challenging scenario of novel view synthesis under noisy conditions, in which each model receives 8 noisy inputs and synthesizes one novel view for 43 bursts extracted from 8 validation scenes. Again, our multiplane feature encoder renderer significantly outperforms the existing methods, IBRNet, IBRNet-N, and noise-aware-nerf. Thank you for your attention. We look forward to meeting you in person on Thursday afternoon at poster location 28.